Hello everyone, today let's take a look at QP108 asking us if a stick is cut twice randomly, what is the probability that the three segments form a triangle? So I have a stick that looks like this, let's just say it's of length L, and I cut it twice randomly, so I'm applying a uniform distribution, so maybe I make a random cut here and a random cut here. So now my stick is broken at these 2 points, and now I have 3 different line segments, so can I form a triangle with these 3 line segments? Well, let's just see visually. First of all, this line right here is roughly this length, and then this line right here might be this length, and then this line right here will be a little bit shorter, so maybe something like this. So can we form a triangle? Well, right now it's not forming a triangle. Basically what I can do is just move this stick down and this one as well until they basically meet, and it's going to look something like this. It's going to be more narrow than that. It might look something like so. So we just did that example by visually looking at these sticks, but you can see that they do form a triangle in this case. So what were the conditions for them to form a triangle? Well, now instead, let's just imagine that my 2 cuts might be over here. So they're both off to one side. So we have 2 very small segments and 1 large one. So can we form a triangle in this case? Well, let's just lay out our segments. We have 2 really small ones. Maybe they look something like this, and we have 1 really long one. And maybe like this, you can see that we do have a triangle, but that does not count because we need basically every single one of these points to be touching another one, right, for a triangle to form. And you can just see that given that I have this really long stick now, these 2 little tiny segments are not going to be enough to meet each other. So we really cannot form a triangle in this case right here, right? So in general, what are the conditions where I can't form a triangle? Well, you can see pretty clearly that basically the stick of longest length, or the segment of longest length when I cut it, is going to pretty much be the biggest factor, the limiting factor. I'm going to need my other 2 segments to be long enough such that they can meet at some point above this line. So these sticks right here would work, but if I made this stick a little bit smaller, well then I need to move this one down a lot to compensate for that so every point could meet. Then if I made either one of these sticks a little bit smaller, let's say I made the right one a little bit smaller, so maybe it's something like this now, well then I need to move these even closer together and have tighter angles right here to order for them to meet, right? So I'd have to have really tiny angles now here, maybe something that looks like this. It's still a triangle if we have basically non-zero angles right here. But the point where I cannot meet any longer are basically when I'm going to have my angles so small that it's basically just going to degenerate into a line, right? In that case, that's not going to be a triangle. So what is that actually mathematically? So at what point did they degenerate into a line? Well, if I call this line segment down here C, and I call my other 2 A and B, they basically degenerated when I had A plus B equal to C. Because at that point, if I draw B in green here, and let's say I draw C in blue, at that point, that was the last point that they did not form a triangle. If I increase their length by even a little bit, well then I could form a triangle with the tiniest possible like little small angle like so. So basically my cutoff point was when A plus B was equal to C, because at that point they at most degenerated into a line. So at this point right here I have no triangle, but if I make A or B even a little bit bigger, then I'm going to be able to form a triangle with the tiniest little possible angle. So when A plus B is greater than C, then we are going to be able to form a triangle. And then finally, in my last remaining case, when A plus B was less than C, well then I'm definitely not going to be able to form a triangle, right? If I made either of these even a little bit smaller, obviously I'm not going to be able to form a triangle in that point. I'm going to be in the case where I basically have 2 little tiny line segments and 1 big one. So the question is asking us about forming a triangle, and the only case where that is going to be true is when A plus B is greater than C. Those are our conditions to form a triangle, where C in this case was basically the length of the longest stick. So that is really the core condition here. When we had these 2 cuts right here, this one was longest, and obviously the sum of these 2 was way less than the length of this one. So in that case, we did not form a triangle, which is what we would expect. But up here, if we take these same 2 cuts, but we just move them kind of down a little bit, then maybe the length of the longest stick is this one now, right? But the sum of these 2 is still going to be greater than it. So in that case, we could form a triangle. And then if we moved our cuts out a little bit further, we still would be able to form a triangle because the length of the longest one, well, they're all pretty close in this case. Let's say this is the longest one now. Well, the sum of these 2 is going to be greater than it. So we still can. But once we get out to the edges, let's say our cuts are right here, well, now this middle one is going to be the longest, and we're not going to be able to form a triangle because these 2 do not sum up to the middle one, right? So this question's a little bit more complicated than it looks, right? We have a bunch of different ways to form a triangle with these 2 cuts. So basically what we can do is just realize that both of our cuts are uniformly distributed, or we can do the exact same thing that we did in QP127 if we let X be the value of our cut number 1. So X could be anywhere within this line, basically from 0 to L, I'm saying, where L is the length of our stick. So it's uniformly distributed between between 0 and L. And then y, our second cut, is also going to be uniformly distributed between 0 and L. So we can plot it like this. Basically, this right here is the land of total probability when I have x equals L and y equals L up here. So their joint distribution would be within this box right here, where basically every single point is going to be equally likely because we have uniform random variables. And again, just like in QP127, if we have basically the probability equal at every single point within this continuous box right here, then we can just think about the probability of a triangle in terms of area. So what is the probability of a triangle within this area here? Well, let's just make some random cut on our line. We're going to call that x, and then another one we're going to call that y. And then first of all, to simplify calculating this probability, we can basically just say, for instance, let's just assume that x came before y on this line right here. So in that case, if we divide our square with this line right here, we're only going to be looking at the top left triangle. First of all, if x is less than y, well, we can say the length of this segment right here formed between L and y is just going to be of length L minus y. Now the length of this segment right here between x and y is going to be of length y minus x, and the length over here is just going to be of length x. Okay, so now the value that we're interested in, the length of the longest stick, is just going to be the maximum of basically all three of these line segments. So L minus y, y minus x, and x. So this is the length of our longest stick, and we know by what we found over here that we basically are just going to need this less than the sum of the other two. But we also know that since we're dealing with a line of length L, where the length of all of these are just going to sum up to L once we sum all these up, obviously. So if we simplify and we just call this C, so C is the maximum of our three line segments, and basically the sum of the other two we'll again just call A plus B. And we also know that the sum of those three line segments have to sum up to L. So basically what we can do is just rearrange this, and we can say that A plus B is just equal to L minus C. And then when we plug that in here, this is what our inequality is going to be, right? C less than L minus C. So basically we have 2C less than L. And we just divide each side by 2. We just get that we need the length of the longest stick to basically be less than the length of the entire stick divided by 2. That's the inequality that we need to satisfy in order to get a triangle to form. So C was just a stand-in for our maximum, so we just need the maximum of L minus y, y minus x, and x to be less than the length of the entire stick divided by 2, and then we'll be able to form a triangle. And that also just makes sense by looking at the line. If we have a line of length L and we have two cuts over here, well then this one's going to be greater than L divided by 2. It's going to be greater than half the length of the total line, so we're not going to be able to form a triangle. But versus if we have something like this, then neither line is going to be greater than half the length of the entire line. So if we need the maximum of these three segments less than L divided by 2, well that just means that we need all three of them to be less than L divided by 2. So we need L minus y to be less than L divided by 2. We need y minus x to be less than L divided by 2. And we need basically x to be less than L divided by 2. So if these three things are satisfied right here, then we're going to be able to form a triangle. So if I come back up to my graph, well let's just graph this stuff. So here's my point L divided by 2 on my x-axis, and here's my point L divided by 2 on my y-axis. So my first condition, I need x less than L divided by 2. So this is L divided by 2, and x is less than L divided by 2 in all of this region right here. Well, you remember also that we impose the constraint that y needs to be greater than x basically. So we're only dealing with this region up here first of all. So we can only really need to shade in this part. And we impose that condition just to make it simpler, right? And then we're just going to use symmetry to find the probability mass on the other side as well. Okay, so that was our first condition right there. Now let's look at our second condition, y minus x less than L divided by 2. So that's just going to be when y is less than x plus L divided by 2. So to plot that, when x equals 0, we have y equal to L divided by 2. And then when x goes up to L divided by 2, y will be L. So we'll basically have all the region under here as well. Technically, this condition right here would be all of this mass right here, but we have our other conditions imposed as well that we need to be true. We need to be greater than this line and basically have the same overlap as this green region. So I'm just going to shade in this part. And now finally, for our third condition right here, we can just rearrange this to be the fact that we need y greater than basically L divided by 2. So how do we draw that? Well, if this is L divided by 2, y being greater, that would be all of this region up here. So basically just this region would be triple overlapped. So boom, the region that satisfies all three of our conditions is made up of this mass right here. When we're just looking at basically half of our total mass, right? When we implied that y was greater than x, that's everything above here. So just this mass in that region. And the mass of this triangle is a region with basically width L divided by 2 and height L divided by 2. So area of a triangle, we just take L divided by 2 times L divided by 2, and we divide that by 2, obviously. This is just going to be equal to L squared divided by 4 divided by 2, which is just going to be equal to L squared divided by 8. So That's the probability that we get a triangle, right, when we're looking at the cases when y is greater than x. If we flip the situation and we had x greater than y, well, you can pretty clearly see that we're going to have symmetry. We're going to have the exact same conditions, right? So we're going to have the exact same probability mass in the other half of this triangle. It's just going to be inverted. It would look something like this, a triangle of mass like so. Now again, since we have a uniform distribution, every point in this joint distribution is going to be equally likely, and when we have that property, we can just take our masses and work with them directly. And again, in the top region, right, when y was greater than x, we had a mass of L squared divided by 8. In the bottom region, by symmetry, we're going to have that exact same mass. So in total, the mass is going to be L squared divided by 8 plus L squared divided by 8. That's just obviously equal to 2 times L squared divided by 8, so just L squared divided by 4. That's the total mass of us basically getting a triangle. Now the total mass of this square right here is just L squared in this situation, right? So the probability of us getting a triangle, our final probability, is just going to be this right here, the mass where we have a triangle divided by the total mass. So L squared divided by 4 divided by L squared, which is just going to be equal to 1/4. You could have also just as easily made this simpler by just setting L equal to 1. And in that case, we'd have a pure probability distribution, right? Where the total mass in here would be 1. And then in that case, if we set L equal to 1, so we know the total mass is 1, then we can just calculate basically the mass of these, and in that case L would be obviously 1, so we'd have 1/2 by 1/2, basically two 1/2 by 1/2 triangles, which would just give us 1/4. So yeah, the probability of us getting a triangle when we break a stick twice, so it cuts it into 3 segments, is going to be 1/4. That is our final answer. So again, just by knowing the fact that these cuts are uniformly distributed, that allows us to basically have an equal probability density in every single region, which just allows us to use areas, which makes this calculation a lot simpler.